So this is the 14th session in the subject of digital communications, and we are going to study threshold calculation in this particular session. In the one of our last sessions, we had studied the basic block diagram for the binary detector, and we had said that after detection, the value must be compared with some threshold in order to find out whether a 1 was transmitted or 0 was transmitted. So that threshold, we want to find out what should be the value of that threshold. That is what we are going to do. So let us start by quickly revising our block diagram for the binary receiver. So the incoming signal is either S1T or S2T based on whether 1 was transmitted or 0 was transmitted, and there is always some noise present. This noise comes in various forms, but one important source of noise is the thermal noise, which we are going to consider. So this gets added to the incoming signal, and the net received signal we call as RT, which is either equal to S1T plus NT or it is equal to S2T plus NT depending on what was transmitted. Then this RT goes through a receiving filter, which is a matched filter, and the job of this matched filter is to maximize the signal to noise ratio so that the detection error probability is minimized. Then you have an equalizer filter, and its job is to reduce the inter-symbol interference. This we have not studied so far. This we had studied in one of our earlier sessions. This we are reserving for a later study. In any case, the incoming signal passes through the matched filter, the equalizer filter, and then at the end of the symbol time or the bit time, you take the decision. So you sample at t equal to capital T, and then this received value is compared with a threshold in order to decide whether 1 was sent or a 0 was sent. And whatever analysis that we will now do is directed towards finding the expression for this threshold. Okay, so let us start. So as we said, the goals of analysis: find out the threshold. Then the analysis can be furthered in order to find out the bit error probability. Although in this session we will concentrate only on threshold, and in the next session we will find out the expression for the bit error probability. Now, in order to find these expressions, we need to revise our knowledge of Gaussian probability density function, because we are considering thermal noise as the main source of the noise, and this has this density function. I am of course assuming on the part of listeners some knowledge of probabilities and probability density functions, etc. But since Gaussian density function is important for us, we'll quickly revise it. So what is the expression for the Gaussian density function? Let's assume that x is some continuous random variable. Since it's a continuous random variable, we cannot talk about the probability that the variable has a particular value that approaches 0. But what we can talk about is the probability density function, and the Gaussian density function is expressed in this fashion. So as you can see, because this is x squared with a negative sign here, the x equal to 0 you will have maximum value, that is 1 upon under root 2 pi, and then it will decrease on both sides. Okay, so it will look like this, as you can see. Now here I have expressed this as a I have considered x as our continuous random variable. I have also written the same expression by using another dummy variable z, and the reason for this is that we want to find the probability that the observed value of x is greater than a specified value of x. So in order to avoid the mathematical confusion, we write the same expression by using another variable, say z, and plot pz as a function of z. So at z equal to 0, this is maximum 1 upon under root 2 pi, and then decreases on both sides. Now we have said that since it's a continuous random variable, we cannot talk about the probability that it has a specific value, but we can find out the probability that the variable lies in a certain range. So the probability that x is greater than equal to x can be obtained by integrating this the probability density function from x to infinity, because this is asymptotic to infinity, asymptotic to 0 as x approaches infinity. So therefore, if we integrate this from x to infinity, we will obtain the probability that the random variable x lies somewhere in the shaded region from x to infinity. So you can now see the reason why we introduce the dummy variable here, so that there is no confusion about the limits. So once you integrate pz and put the limits clearly, what you will get will be a function of x, and it is typically specified as qx. So the probability that x, the observed value, is greater than equal to a certain possible value x is equal to qx, and it's given. So a lot of results are often written in terms of qx, and that is why this is an important expression. Okay. Now that was a normalized Gaussian density function. Let us see the general form of the Gaussian function. It looks like this. See, in the normalized version m was 0, but if m is the average value of the random variable, then this gets changed to x minus m whole squared rather than x squared. Also, sigma x is the standard deviation of the random variable, and in the normalized this was assumed to be 1. So if you have a random variable whose average value is m and the standard deviation is sigma x, then the probability that x is greater than x can be written as q of x minus m by sigma x. So if this is known, m is known, sigma x is known, so this term can be calculated, and then by using the tables we shall see soon, it will be possible for us to get this. Okay, so this is our normalized function. This is a more general form where the maximum occurs at z equal to m and not equal to 0. Okay, and also if the standard deviation is smaller, then it will look like this. So these are the examples of the more generalized Gaussian function. This is the normalized Gaussian function. Okay. Now, how to obtain this qx? So we don't have a closed form solution, but approximate expressions are available. So if x is much greater than 1, you can use this expression. Note that the only difference between this and the density function is division by x here. But if x is greater than 2, suppose it's not much greater than 1, but just greater than 2, then this is the expression that can be used in order to find the qx. Okay. These two expressions can be used, or very often people use tables. So this is a table. You can pause the video at this point, and whenever you need the table, you can look at the values. For in the table, one entry is x and the other is qx. So x equal to 0, clearly since the Gaussian density function is symmetric around x equal to 0, the qx, the probability will be 0.5. And as x goes on increasing, you can imagine that area goes on decreasing and this will reduce. So as x increases, qx will go on reducing. Okay. Now one more term we would like to study before we go further is that many of the signals that we encounter in communications are ergodic signals. So what is the meaning of this term ergodic signals? Meaning is that when the signal has a statistical and time average which is same, then it's called as an ergodic signal. To get some feeling for this, suppose this represents a noise voltage across a resistor of a certain value connected to a circuit of definite bandwidth. Then the instantaneous value of the noise will be random and may look something like this. But if we consider an identical resistor connected to the identical circuit, still since this is a random one, the waveform that you will get will still be a random. It will not be necessarily exactly equal to this. So you can think of large number of collection of resistors, and for a given time you can consider the samples. So once you consider all these samples, you can apply statistical averages rules and calculate the statistical average, mean square value and so on. Or you can take only one waveform and calculate time averages. That is, what is the average value considered the independent variable as time, what is the mean squared value, and so on. And as far as we are concerned, most of the signals that we will be dealing with are the ergodic signals. So whether you consider a statistical average or you consider a time average, both are going to be same. So we'll use them interchangeably often. Okay. So statistical average will also mean the DC component of the signal. That is what it means. Okay. Now let us define some of the threshold computation probabilities. So probability that the received signal is S1, probability that the transmitted signal was S1 given that the received value is Z, that we call as the probability. And clearly this is a discrete probability because either S1 was sent or S2 was sent. So this is a conditional probability, and which means that this is the probability that the transmitted signal was S1 given that the received signal is Z. So clearly this is a discrete probability, as we said. Then PS2 stroke Z, this is the probability that S2 was transmitted given that the received value is Z. This is a discrete probability as usual. For PS1 by Z is a discrete probability, and so is PS2 by Z. So the question is, how do you decide whether S1 was transmitted or S2 was transmitted? So you decide that by looking at the conditional probability. So if PS1 by Z is greater than PS2 by Z, then you conclude that S1 was transmitted. But if PS1 by Z is less than PS2 by Z, then you conclude that S2 was transmitted. And this is called as a map rule or maximum a posteriori criteria. A posteriori means that considering that the received value was Z, the probability of S1 has a certain value. So that is why it's called as a posteriori. So it's basically a conditional probability. And these two inequalities together is called as a maximum a posteriori criteria or the map rule. Now what we want to do is to obtain the expressions for PS1 by Z and PS2 by Z, so that we'll be able to calculate the threshold. Okay, so whatever next we now do is directed towards finding the expression for the threshold. Let's start with that. So Z is a continuous variable because of channel distortion and noise. That is the detected signal at the end of the symbol time period, and it's a continuous variable. Therefore, since this is a continuous variable, you cannot use discrete probability for this. You have to use a probability density function. But this is a conditional probability density function. Given that S1 is transmitted, Pz by S1 is the probability density function. Similarly, Pz stroke S2, this is the probability density function given that S2 is transmitted. Now the reason we are defining these probabilities is because we shall see that it will be possible for us to write down the expressions for these, and once we relate these to the discrete probability that we have studied in the last slide, we'll be able to obtain the threshold. For that reason, this is studied. So this, whether you consider this or this, you call this as a likelihood of S1 or S2. So this is the likelihood of S1, this is the likelihood of S2, probability density functions. Okay. So what we want to do is to obtain the relation between these two probability density functions and the two discrete probabilities that we have studied earlier. Okay. So we already said this is our map rule. Now we use the mixed form of Bayes theorem. So Bayes theorem, so those of you who have studied probability theory, and I am of course assuming that the listener has some knowledge of probability theory. This is the form of the Bayes theorem. PA stroke B into PB is equal to PA dot PB stroke A. Now mixed form of Bayes theorem, mixed because one of the probabilities is discrete and the other is the probability density function. So by looking at this, by analogy, we write down the mixed form of Bayes theorem. So that is P S1 stroke Z into PZ. So that is analogous to this A stroke B PV is equal to P S1. So that is PA PZ stroke S1 PB by A. Okay. So then in that case, PS1 stroke Z, this PZ comes on this side. So you get PS1 PZ stroke S1 divided by PZ. And similarly, we can write PS2 stroke Z PZ is equal to this. Or PS2 stroke Z is this PZ comes on this side. So now, when we apply the map rule, what we get? PS1 into PZ stroke S1 is greater than this. This is the map rule. You can see this. This is PS1Z greater than this. So PS1Z is given by this. PS2Z is given by this. So when we substitute these two equations in this inequality, PZ is common, that cancels, and we get PS1 PZ stroke S1 greater than PS2 PZ stroke S2. That is our map rule expressed in a different fashion. Or we can write it like this in terms of the likelihood ratios, that is PZ stroke S1. See, I have brought it on this side and PS1 on this side. So this is given by this. So P probability that the transmitted signal is S2 divided by the probability that transmitted signal is S1. This of course it depends on the source distribution. And we'll write down the expressions for this and then obtain the threshold. Okay. So I have repeated that here. If now let us assume a specific condition which is often true. PS1 is equal to PS2. So this right hand side will be 1. So you get the criteria PZ stroke S1 upon PZ stroke S2 greater than 1, then S1 was transmitted, else S2 was transmitted. So now it's a question of writing the expressions for these conditional probabilities, substituting in this inequality, and then finding the threshold. Therefore, let us see how PZ by stroke PZ stroke S1, how it will look like. Note that it is a conditional probability density function, conditional density function, and since Z is a continuous variable, but it's a random variable because noise gets added, and we have seen that the thermal noise has a Gaussian density function, so this will also have the Gaussian density function. So then we can write the okay, so whatever I have been saying is sort of concluded here. When S1 is transmitted, the output from that final sample block is A1, and then this is the filtered value of the signal, this is the filtered value of the noise at the output where we are taking the sample. Okay. So average value of Z, since the average value of N0 is 0, this is same as A1. And the sigma Z squared, mean squared value is Z minus A1 whole squared, its average. Okay. So we substitute for Z, so that is A1 plus N0 minus A1 whole squared. So A1 cancels. So that is N0 squared average, and that is sigma N squared. This is the mean square value of the noise. Okay. So then density functions can be written like this. PZ stroke S1. So if S1 was transmitted, the detected value will be A1. Sigma N is of course same. But if S2 was transmitted, the detected value will be A2, and you get these two density functions. So only difference between these two is that here you got A1 because S1 was transmitted, and here you get A2 because S2 was transmitted. So now we apply the map rule in order to get the threshold. So PZ upon PZ stroke S1 upon PZ stroke S2, if you substitute in those equations, you will get this. So if this ratio is greater than 1, S1, then S1 was transmitted, else S2, map rule. So We write it like this: if this is greater than 1. So now concentrate on these two terms. In order to simplify this, what we do is we take the natural logarithm of both sides. So the right hand side logarithm will be equal to 0, and the left hand side logarithm, since the base is e itself, it will be equal to this exponent itself. So this exponent has to be greater than 0 for this condition to be fulfilled. So it's easy to see, I'll leave it to the viewer to work it out. It's easy to see that it can be now condensed to this form. So taking logarithm of both sides and rearranging, we get our threshold, that is Z is greater than a1 plus a2 by 2, then s1 else s2. Thus a1 plus a2 by 2 is the threshold, but this assumes that ps1 is equal to ps2, that is your source distribution is uniform. If this is not the case, then you will have to find a new expression by using the more general criteria pz stroke s1 divided by pz stroke s2 greater than ps2 by ps1. So here we assume that this is equal to this, but if that is not the case, then you have to use this expression and find a new expression for the threshold. So that's all in this particular session. In this session, we have seen how to calculate the threshold in order to make the detection after the sampling in the binary receiver. And that's all.